Hi everyone, I am Rajdeep. I'm currently teaching at Cheenta. Today we'll talk about a very interesting, very important, very simple idea that shows up when we are learning calculus, and that idea is called the intermediate value theorem. It's a result that holds for continuous real valued functions, and it's a very simple idea, very intuitive idea, which essentially just says that if a function, a continuous function, which is a function which whose graph you can draw without lifting your finger, essentially, and so it's almost built into in the understanding of the continuity of the function that if you take a value, say at point A, if you take a value, say C1, and at point B, if you take a value C2, while you trace some sort of a curve between A and B, you will hit every single value between C1 and C2. That's the entire idea. And so if by chance it so happens that at A, your continuous function takes a negative value, and at point B, your function takes a positive value, then no matter how, you can do this yourself, you can take a piece of paper, have a line, and have a point below the line and have a point above the line, and try to draw an unbroken curve between these 2 points. You'll see that it's quite obvious that you can't draw an unbroken line, an unbroken curve between these 2 points without at some point crossing that line you draw initially. And in the case of a continuous real valued function, this line is the y is equal to 0 line. So what intermediate value theorem would mean in this case is that if you had a function, a continuous function, which takes a negative value at some point, A, and takes a positive value at some other point, B, then between those 2 points, A and B, there's some point, C, at which the continuous function is 0. And we'll see this through a problem that showed up in this year's CMI B.Sc entrance about polynomials. And as you would know, polynomials are continuous functions. So we can apply the intermediate value theorem there and find the zeros of the polynomial by seeing where the sign changes. So that's what we're going to see today. So the problem we are looking at today is from the CMI B.Sc entrance exam 2024. This is an objective question. It's question number 2, came this year. So it's a 3-part problem. The part with the intermediate value theorem is this one. So we'll not go over these 2, but I can quickly say how you would solve them if you wanted to. This is a simple application of what we call the remainder theorem. You simply plug in x is equal to -1 into the polynomial and see what the value comes up. The second question, this one, is solved by using a simple application of Vieta's theorem. And the question that we really care about right now is this one. So what's given is that you have a polynomial px in this form, and you want to find an integer n with the least possible absolute value, so as close to 0 as possible, such that px has a real root between n and n plus 1. So you want to find the 0 of px closest to 0 itself, and you want to describe that 0 using its closest integers. So, if your polynomial looked like this, you know that starting from 0, this is, say, 0, and say this is 1, and say this is 2, and so this is 3, then the integer you're looking for is 1. So that's what you want to do. And in the exam, the way this question came is you would have written your answer, you would have submitted your answer as whatever n you think the answer is, comma, what number theorem out of these 5 you are going to use. In our case, this is going to be the intermediate value theorem. So we have this polynomial, p of x, and we want to essentially find a 0. And we want it to be as close to 0 as possible. So if by some miracle the 0 is 0 itself, that'd be as great as it gets. So let's check. Is p of 0 0? So let me just write down what the polynomial is. So let's check the value at 0, right? At 0, the value is, I don't have to look at any of these guys because when I put x is equal to 0 in this part, in fact, even this, and x is equal to 0 when I set x is equal to 0, this entire part just goes away, right? So p of 0, as usual, is just going to be the constant term. Unfortunately, this is not a 0. The value is negative 11. What would be great is if somehow p of 1 was greater than 0. That would be really nice, because then our answer would be 0, right? And that's exactly what intermediate valuing theorem is. That we know that p of 0 is negative 11. If it turned out that p of 1 was something positive, I don't know, say 5, I'm not saying it is, but for now, let's pretend it is, then the polynomial would have to look something like this, right? The point is that it's a continuous function which takes a negative value at one point and a positive value at another. And so in between, it has to cross the x-axis and it has to take the value 0. And so this is where our optimal 0 would be, right? We want it to be as close to 0 as possible. And so all that remains to see is p of 1 actually greater than 0. So p of 1, when we plug it in, is going to be 1 to the 6 plus 10 times 1 to the 5 plus 11 times 1 to the 4 plus 12 times 1 cube is 13 times square minus 12 into 1 makes 11. And it doesn't take a lot of work. So the 1 plus 10 cancels out with the minus 11. We have an 11 here, we have a 12 here, a 13 here, and a minus 12. So these will also just cancel, and you just have 24, just decidedly greater than 0. And so we get that at 1, the value of the polynomial is 24. And so we have a 0 between 0 and 1, somewhere over here. And our answer is, in fact, 0, because we wanted to find n with the least possible absolute value so that px has a real root. And so n would be 0. So this is how we usually approach problems. It's in fact a general strategy with polynomials. In even as far as complex analysis, which is a higher topic, you kind of do the same thing. You use the results you have that you know about polynomials, and so in general, even something like a topic like Descartes' rule of signs, it essentially tracks the sign changes. So with polynomials, tracking zeros is essentially the same data as tracking sign changes, where the polynomial is negative and where the polynomial is positive, because you know that wherever there's a sign change, there's a 0. And so this is a very important idea using which you can find zeros of a polynomial. Thank you for watching. Have a good day.